First of all, I want to say thank you for inviting me here. This is my second time in Korea and my first time in Alma, Korea. I will begin with a small introduction about Alma Lasers. This is our campus in Caesarea, Israel. In this campus, there is the management, the R&D, and the manufacturing. All the development and all the manufacturing of Alma Laser is being done in this site in Caesarea. Alma Laser was established, as you know, in 1999. And since then, we are producing RF system, ultrasound system, and many laser systems. As of today, we have 900 employees in Alma Lasers. And the CEO of Alma Laser is, of course, Mr. Lior Dayan. I'm the EVP of the R&D. I have 80 employees that working in the R&D. I'm in Alma Lasers for 18 years and 8 months already, but who's counting? Before that, I worked for other medical devices as well. And what we are going to speak today? Today we are going to speak about laser diodes. A little bit about technical side of the laser diode, and also how in Alma Laser, how in the R&D we are thinking when we are doing a new machine, when we are developing what is important for us, what is not important for us, just that you will get the sense of what we are doing and how we are doing the things we will do. So basically, diode laser. Diode laser is, first of all, a diode. A diode is an electrical component. You can find it in every circuit board that you take into your hand, even in your watch, even in your cell phones, you can find a diode, electronic diode. Basically, in electronic diode, you have two plates, P plate and N plate. P is for positive, N for negative. The purpose of the electrical diode is to make sure the electrical current will go only in one direction without a backlash to go back. And how we do it? When we have a negative in one place and positive in other place, if we connect in the negative a positive line and the opposite here, the negative and the positive will come together. So in the middle, you will have a gap. So will not be any closing circuit. You will have a cutoff. But if you connect it correctly, a plus to the plus, a negative to the negative, you can close the circuit and the current will flow. This is simple electrical component. But once we want to make it a laser diode, we are using the same N-type and T-type plate. But in the middle, we are adding an active layer. The active layer is the active where the photon is being created. So when we have an active plate, we also have the electrical current running in the diode, and the photon is being created and is going back and forth inside the diode, and eventually will go out through a certain place that we will let him to go out from. The wavelength of a diode is being made by the active layer. So you need to change the material of the active layer in order to get a different wavelength. Up to now, it's very simple. Let's see a little bit of pictures. This is one bar of laser diode, very low emission, so we can take a picture. Actually, you can see here that the laser is coming from spots. These spots called emitters. The area of the diode can be covered by 30% emitters up to 90% emitters. This is basic knowledge. I will go back to that at the end, okay? Just remember that. Also, you should know that the efficiency of a laser diode, more or less 50%. What does it mean? If you will take 200 watt and run it through a laser diode, you will get 100, if you take 200 watt, you will get 100 watt of laser and 100 watt of heat. The heat you need to take out of the laser. This is very important to remember. We will speak about it later in the lecture. This is a schematic picture of our diode. Our diode has bars of lasers. We run electric current, and we have a system that cooling the diode. We are using a DI water. But you need to know one thing. We are buying our diode from one supplier in the United States. The only one who can buy the titanium diode is Alma Lasers. If someone will try to connect with that supplier in the United States and buy our diode, I will get a phone call about 1 hour later, and I will get the name of who's trying to buy the diode. And why is that? Because we worked with that company in order to develop this kind of diode. You will understand later what is so unique about our diode. So we have a water for cooling, a DI water. We do not use nothing else. A DI water, and the quality of the DI water is very important for the cooling of the diode. Okay, next change. When we have the basics, we need to know how to operate a laser diode. There are two ways in general to operate a laser diode. The first way, simple one, you take a capacitor, you charge the capacitor with electricity, and then you discharge the capacitor to the diode. The second one is to have a much complicated system that you will have a constant current all the time. So what is the pros and cons of each one? This one, the best thing about it, it's cheap. You can buy it everywhere. Just buy a couple of capacitors, small power supply, and you're all set. You can drive it. But the electric current will decrease in time as the voltage will decrease from the capacitor. That means that if you will try, if you want to have a pulse of laser, and you want to know how much laser will go out, you need to take into consideration that from the start point you will start the lasing until the point you will end the lasing, the amount of laser, the power will go down. In this configuration, you have a constant current. You don't need to worry. You have the time. You know exactly how much power you will get. Also, if you try to do a higher repetition rate with this kind of system, in order to get your power, you need to overshoot. That means if you are aiming for, let's say, 100 watt, and you have certain time, you need to overshoot in order to get the amount of power you like. When you overshoot the current, overshoot the energy, you also have an overshoot in the temperature of the diode. Once you have an overshoot in the temperature of the diode, the lifetime of the diode will decrease. The lifetime of the diode is dependent on the temperature and the current it's running in. It's most important. This system, the cons of this system is the price. But in the R&D, we do not care about the money. So if we see that this is the best thing to do the job we need, we will choose that. So of course, we choose this one. Now we need to talk about a little bit the process of how to do the design itself. So once we decided to go with the constant current, we need first power supply, cooling system, and of course in every system we are doing, safety. Power supply. What do we need? We need a stable power supply. Each time we want to give a certain current, we need to know we will get the specified current we like. Not a little bit high, not a little bit low, not with spikes, even not little spikes. And we need to control the current. So what do we have in the titanium? In the titanium, we have the best power supply we know in the market. Japanese brand. We are not dealing with any other kinds of manufacture. I know that some companies in the market are telling that Alma is using something else. No, I'm telling you we are using only Japanese source for power supply. And we need much more energy from our power supply compared to the previous soprano, the platinum. So we've done it. And because of these two things, and of course the cooling system we will speak, we are able to get a lifetime for the diode. Okay, now we got to the cooling. We need a steady cooling. When you are running a diode, the diode wants to be in a certain temperature. If you increase from this temperature, you will hurt its lifetime. If you decrease from this current temperature, you will decrease the lifetime as well. I will speak about it later. And of course, we need a good quality of water in order to take the heat from the diode. So we use a deionized water, but in a very strict condition. What do we have in the titanium? In the titanium, we choose to work with a compressor, but not any kind of compressor. You know it maybe from the air conditioning. We use inverter. And why we use inverter? We use inverter because not all of you use the highest amount of power you can get out of the machine. And as I said, you want the diode to be in a certain temperature. So if you are not in 10 joules, you are in 5 joules. We need to take less heat from the diode. So we need to use inverter. We need to know how much heat we are taking in every certain moment from the diode itself. And this is what we have. And also, if you maybe know, wavelength of the diode can shift. A little bit to the right, to the left, a little bit to the right. But when you have a certain, you can keep the temperature steady, you don't have shift in the wavelengths. So we use in the soprano a compressor, and a very good one, to control the temperature of the water. In the past, we used to have a passive system to take the heat out of the diode. A passive cooling system, it's actually like you have in the car with a radiator. But the problem with this kind of a system, you cannot control the temperature. If the room temperature is 30 degrees, you cannot get in the diode less than 30 degrees. It's that simple. So we chose the compressor and inverter one. Safety. Safety, I think, is most important for all of us. We don't like to have adverse events. We want to be sure that our machine will deliver the things we wanted to deliver. If it's temperature, if it's power, everything. So what do we have in the titanium? We are monitoring in the titanium everything. We know the amount of flow of water. We know the temperature in the compressor. We know the temperature inside the handpiece itself. We know the amount of current we are using in each time. We know when the current started, when it ends. We measure the pulse wave. We measure everything in real time. Okay. A little bit of history. In 2002, we started with a laser diode that we called Mythos 500. It was 1 by 1 centimeters. I think it ran about something like 1 hertz or 2 hertz, not faster than that. Then we came out in 2006 with the SHR in motion technology with the first titanium. I started to work in Alma Laser. I was brought to Alma to work on the first titanium. They gave me a project to do the first titanium in 6 months. It was challenging, but rewarding as well. Then we have 7 generations until we reach the titanium. From each soprano to each soprano, we are learning and learning and learning and learning. And each time, we're doing modification and doing it better and better and better. Okay, I mentioned SHR. So let's speak what is SHR. SHR, when we are using low fluence in a high repetition rate, and of course we're using cooling. And why we are doing it? The human body is like a capacitor of heat. It can accumulate certain amount of heat. And it has a coefficient time, in which we can insert heat inside the body. So we can try to do it in a peak power, but as you know, most of the ablation laser using high peak power to get ablation. We do not want to get ablation, but we want a higher energy. So when we are using low fluence in high repetition rate, we can accumulate the heat in certain area. So before the treatment, we're marking the area and working in motion on all the area and making sure that from one end to the area to the other end to the area, we will not lose the temperature. So we all the time increasing the temperature and increasing the temperature and increasing the temperature, but in a safety way. We maintain the safety all the time. This is very important. So what are we getting? We're getting less pain because we are losing low fluence. We're getting safety because we are in low fluence. And better coverage. You know that in hair removal, in the past we used, and other companies as well, using HR mode. When you're taking one area, do a pulse, moving to another area, and doing a pulse. You cannot overlap between the areas. If you overlap, you will get burns. So in Israel, when we are doing SHR and HR, we can tell the difference about a couple of weeks later. We can look at the body and see that if you've done HR, in between of the pulse, you get small hairs, like a chicken. When he's growing his feathers, he has little feather here, little feather there. So we call him chicken. With SHR, because you're all the time moving, you're covering all the area. So this is the three things we are achieving in the SHR and in motion mode. Okay, about the three wavelengths. Why to do three wavelengths? At the beginning, I thought it's simple. It understood why to do it. But I'll explain. In the past, the old past, the hair removal started with 1064 wavelengths. When we targeted the blood supply to the hair, because the 1064 has a lot of absorption in the water, it was okay, but it did not treat everything. Then after we used the 1064 and the YAG in the industry, they moved to 755 nanometer, alexandrite. Alexandrite has a lot of absorption in the melanin. So you can treat the fine hair on the upper of the skin, upper layer of the skin, but it doesn't penetrate too much. Then the industry came out with 810 diode. The 810 diode was good, very good. But still, at the end of the treatment, doctor used to tell us the fine hair is not so much, and we need a longer pulse duration for the darker skin. It's nice, but all of them together is perfect. So this is the reason. It's a very simple one. But once you're trying to combine three wavelengths together, you need to take care of the safety. Because wavelengths, waves at all, they can interact with each other. They can make themselves bigger, and they can destroy themselves. So we need to make sure we are safe, first of all. So what have we done? You will meet Sharon later. The Department of Sharon made this clinical trial. We made a clinical trial on pigs. And we took a square area, 5 by 5.5, and divided it to 4. The upper left, 1064, 755, 810, and trio. And we measure the temperature on the skin. Not so complex. You immediately see the 1064. You can see it immediately. But you can also see in the results that the trio wavelength is as safe as the 755. So once we are safe, we can continue in the development process. But we're also using the soprano for lifting. And when you use for lifting, you want heat. And you wish to get the heat fast. So the question is, can we make the heat faster to make the treatment shorter? We check it as well. You saw also in the previous slide on the pig, we cannot use more energy in the 1064. If we will use more energy in the 1064, we will get a focal erythema. So once we have this covered, we need to discuss about the depth and penetration. When we like to get lifting, we want all the skin to be in a certain temperature. We don't like to hit only one place in the skin. So you can see clearly that the 755 is the shallow of them all. Then we have the 810, and then we have the 1064. 1064, we know from the past it penetrates the most of them all. And of course, we like all the skin, from the upper side to the lower side, to be heated. But you can ask me, Itay, there's a big gap here. You need to address this. Okay, so I will explain. We know, don't forget, that the 1064 making more heat than the 755 and the 810. So actually, from the 1064, we are getting enough heat, because it's more than the 810, the 55, to bridge this gap. But we also need to take care of the upper layer, the 755. And this way, we are achieving the most effective heating to all depth of the skin. And now we need to speak about what we have in the diode. A little bit technology as well. So actually we have 1064, 810, 755, and so on, and so on, and so on, and so on. So people may think that it's logical to do it. And it's logical to get 1:1:1 ratio between the 1064, 808, and the 755. But it's not rational. Actually, to make a laser diode in 755 is hard. Many of the companies that making laser diode cannot make 755. It was a major breakthrough to make the 755. And when we are making the 755, we have less efficiency. That means if we are running into the diode 100 watt, we will get less 755. We will not get 1:1:1 ratio. The most efficiency is the 1064 from the three of them. So why we like 1:1:1? Because we've done measurement and ran it, and we saw that we need 1:1:1 ratio, but it's not easy to do. You remember at the beginning, I told you we will go back to how the laser is working. So why other companies cannot buy our diode? What is the secret? How do we do 1:1:1 ratio? I will run fast. We have our own recipe with the manufacturer of the amount of emitters in each bar we are using. And also we use a different kind of a material inside in the active layer to get at the 755. We are doing it from two reasons. First, we want the 1:1:1 ratio. Second, we want each and every diode bar to be in the same temperature as the other diode bar in the same stack, because we need to dissipate the heat from the diode itself in the most efficient way. And we need to make sure that each bar will live as much as we like them to live. So if someone wants to make a diode like us, I think he has a lot to work on. The price is not important. We already concluded that in the first second slide when I said in the R&D we do not count money. So from my point of view, less important. We have the job to do. And if it's doing the job in the most efficient way, this is the most important, and we need to keep safety. Okay, before we will talk about that, let me talk a little bit about lifetime of a diode. In every manufacturer, you can have a specification of a diode. In the specification, you will get, let's say, 1,000 hours of laser diode. How they measure it? When you buy a car, let's say you buy a Tesla, you will get told in the dealership that you can run it for 600 kilometers. But after you're buying the car, it will not run for 600 kilometers. Because the manufacturer, when he's doing the test of the car, he's removing all the weight from the car. And there's not room for the friction. So it's not really real life. You can compare it to other because the other doing the same, but it's not real life. When we are doing the diode, we are forcing the manufacturer to do the life test under our condition. Not his condition, our condition. So we can control the lifetime of the diode. And also you can buy a diode and they will tell you it's, I don't know, 5,000 watt diode. But under which condition? 10,000 ampere? Okay, you can run it in 10,000 ampere. For how long? For 5 milliseconds? Run it for 5 milliseconds. What do we care? We know the numbers. We know how much watt we need in order to do the job. And we know the life cycle of our diode. So our diodes are running for the lifetime in the same environmental state and the same condition that we are using the diode in the doctor clinic. That means that if we need to run the diode and get some of the laser back into the diode, we are doing it in the tests. We need to do it. We need to know the truth. This is how I see it. A little bit about SHR and SHR stack. SHR 10 Hertz actually is very simple. In 1 second, you have 10 pulses. Okay, Hertz is 1 divided by second. SHR stack 5 at 10 Hertz. That means you have 5 pulses in 10 Hertz, then a relaxation time, and then again 5 pulses in 10 Hertz. And as well, the SHR4 is the same as 5, but instead of 5 pulses, you will get 4 pulses. Also 3 and 2. That's it for the SHR. And actually, that's it.